Hello friends, so far we have learned some basic topics in quantum mechanics. In this lecture, we are going to visualize some of the most important things discussed so far using Python. In case you have never done any Python programming before, I shall provide some basic training. However, since this is not a course on Python, I shall discuss only bare minimum required for our purpose. Throughout the course, Google Collaboratory is going to be used for writing and running the Python codes. You don't need to install any additional software. All you need is a Google account and you can write and run your codes in your web browser. We start our discussion on list and array because they are needed to deal with vectors and matrices. First, to import the necessary libraries. We need NumPy library for mathematical operations and matplotlib.pyplot for plotting. Let us create a vector with 3 components. V is equals to 1, 2, and 3. Now we can calculate the length of the vector. We have to take the first component and calculate its square. So this is how you calculate the square. And similarly for the second and third component, you calculate the square. And then finally you add all of them and you calculate the square root. And for calculating the square root, we need NumPy library. Note that since we are using the function square root from NumPy library, we have to use this word np to call it. Any function from NumPy library will be called with this word np. We can do several operations with list, like finding the maximum value, finding the minimum value, finding the number of elements in the list, and finding the sum of all the elements in the list, etc. Now, these print statements will print several messages as required by us. Let us run the code and see the output. So to run the code, you just have to click this button which shows the arrow. Now we have the output. The first line says that this is a list and this is an outcome of this line, this print command. And the second line just prints the vector and this is an outcome of this print command. The third line prints the magnitude of the vector and this is an outcome of this print command. The fourth line prints the maximum of all the elements and that is an outcome of this print command. The fifth line prints the minimum value and that is an outcome of this print command. Then we are printing the total number of elements and that is outcome of this command. And finally, sum of all elements and that is outcome of this print command. For mathematical operations, arrays are more convenient than list. However, arrays can store only one type of data. This is why when we create an array, we have to mention the data type. For example, it can be an integer or it can be a float. In this example, we create a 1D array containing 3 elements and the data type is integer. This is a vector with 3 elements. Next, we create a 2x2 matrix. We cannot do this using a list and we have to use array for this purpose. We are using NumPy library for doing this. In the previous case also, we used NumPy library for doing this. Next, we can create a 2x2 matrix from 2 different lists. For example, first we define two lists, R1 and R2. And then again, with the help of a function in the NumPy library, we can convert these two arrays to two different rows in the matrix. Let us run the code and see the output. So the first line says that this is an array and this is an outcome of this print command. The next line prints the elements of the array and all of them are 0 because that's what we have defined here, np.zeros. That means it will create a vector where all the elements are zeros. So the next line is just printing all the elements of the array and this is outcome of this print command. Next, the third line, again, it prints the class as array and this is outcome of this print command. And then we are just printing the elements of the matrix and this is what we have done, np.ones. So that means it will create a 2 cross 2 matrix with all the elements equal to 1 and that is what it is printing. And this is an outcome of this print command. And then we print another matrix and this is an outcome of this print command. Just now we saw an example of creating an array from multiple lists. We can also create multiple lists from an array. For example, first we create an array like this. This is a 3 cross 3 array. And then we can convert each row of this matrix to a list using this command. So let us run and see the output. Now you see that it has converted the first row of the matrix to a list. We can do it for the second row as well. And to do that, we have to make these changes, run the code again, and then you see that the second row has been converted to a list. Next, we learn to plot a function. This is going to be one of the most important examples, and I shall demonstrate it very carefully. Let's assume I want to plot fx is equals to sin x from x equal to 0 to x equal to 2 pi. First, we create an equally spaced grid having 100 points using this command. And we are using utilities from the NumPy library for doing this. So this will create a grid of 100 points between 0 to 2 pi. Note that we also take the value of pi from NumPy library. Then we define the functions which needs to be plotted. So for example, we define y is equals to cos x and y is equals to sin x, and see that we are using NumPy even for defining the functions. Then we plot using utilities from matplotlib.pyplot. And this is the command where we are plotting the functions. And then these are the rest of the things like for marking the x level, marking the y level, and then you can also like label the plots, and then finally you can plot it. So let us run the code and see the output. Let us do this step by step. First, we define the range. It is from 0 to 2 pi. And we want 100 grid points between 0 and 2 pi. Next, we define the functions to be plotted. Cosine of x and then sine of x. Next, we plot the function. So x versus y, and we can also label it. This is cos of x. Now, let us run the code. Finally, we have enough skills to plot something we have studied in the course. We start with probability density of particle in a box. The eigenfunction is given by psi n of x is equals to square root of 2 by L sine n pi x by L. Now we take L equal to pi such that the eigenfunction is psi n of x is equals to square root of 2 by pi sine nx. We want to plot mod psi n square for any given value of n. In this section, the user has to input the value of n, and then we create equally spaced grid point. Now in this part, we define the functions, and then in this part we plot the functions. So let us do it. Portion of the code is already written. Let me enter one of the eigenfunctions. So this is square root of 2 divided by pi sine n1 x. And the eigenfunction for n2 is already given here. Now let us run the code and see the output. So it is asking us to enter the index of the first wave function. So let us enter some small value. Then it is asking for the index of the second eigenfunction. Let us enter a bigger value. And finally, you can see the plot of the probability density for n1 equal to 2 and for n2 equal to 10. Let us calculate the position uncertainty for a given eigenfunction. To calculate the position uncertainty, first we have to calculate the expectation value of x. Next, we have to calculate the expectation value of x square, and from that we can calculate the position uncertainty. The expectation value of x is given by integral 0 to pi x psi n square x dx. The expectation value of x square is given by integral 0 to pi x square psi n square x dx. Remember that we are taking the box length to be equal to pi. Now we are going to evaluate these integrals by using some numerical technique. We are going to use trapezoidal rule to evaluate the integrals numerically, and we are going to use SciPy library for that purpose. So first, the user has to give the index of the eigenfunction, then a equally spaced grid is created, and then we define the eigenfunction here, and this is same as this, right? We are using L equal to pi. Now in this step we evaluate the first integral x psi n square x dx. In the next step we calculate the second integral x square psi n square dx, and then in this step we calculate this value, and then the code writes the calculated value. Let us run the code. So we have to enter the index of the eigenfunction. So let us enter 1, and then you see the position uncertainty is this. Let us try one more value, and let us try 2, and the position uncertainty is given by this. Before proceeding further, let us enhance our coding skill a little bit. We have to learn about user-defined function for loop and if loop. We are going to write a code to verify whether some function has a root in some given range. Let us understand the algorithm first. If we plot the function fx is equals to sin x by x, this is how it looks like. A root exists at every point where the function is equal to 0. Note that fx changes sign from positive to negative or negative to positive as it crosses the point where it has a root. Thus, if we take the value of the function just before and just after the root and multiply, I should get a negative number. For example, if I take the value of the function at this point, and if I take the value of the function at this point and multiply these two values, I should get a negative number. This is the algorithm for finding the root. Now, let us understand the code. The range needs to be defined here. Then we define a function such that it returns the value sin x by x for a given value of x. Then we create equally spaced breakpoints and then we run a for loop to check whether the product of two consecutive values of the function is less than 0 or not. So here we take two consecutive values of the function f at point I and point I plus 1 and then check whether the product that is calculated here, whether that is less than 0 or not. If it is less than 0, then we know that there is a root. So at that point, the loop stops and the value of the root is printed. So let us run the code. So here at this point, we have to define the function sin x by x. The function is to return this value. So once we have defined the function, then we create the equally spaced grid points between x1 and x2. And then we run a for loop. And then we have to call the user defined function that we have defined here, f of x. So this is how you call the function f and then you give the value of x. And what we want to check here, whether the product of two consecutive values of the function is less than 0 or not. So we just do this, right? So this is the value of the function at a point x of I, and this is the value of the function at a point xi plus 1. And we have to check whether the product is less than 0 or not. And for that, we use the if statement. And if the condition is true, right? For example, if the product is less than 0, in that case, I just print the value of the root. And then the break statement tells to stop the for loop once we have found the correct root. So let us now run the code. Before we do that, let me just show you the plot of this sin x by x. This is how it looks like. So for example, if we check a point between like 2 and 5, then we surely know that there is a root. So let us just check that. The lower bound is 2, the upper bound is 5, and the root is at 3.14. Let us check one more point. And again, we see that if we check between 5 and 7, then we surely have a root. So let us do that. Lower bound is 5 and the upper bound is 7. and the root is at this point. Let us now calculate the momentum uncertainty for eigenfunctions of particle in a box. We know that this is the momentum operator and expectation value of P is given by this integral. Essentially, we have to calculate the integral of psi of x times psi dashed of x in the limit 0 to pi, because the length of the box is taken to be equal to pi. Psi of x is given by sine of nx times square root of 2 by pi, and similarly psi n dashed of x is cos of nx times the appropriate constant. Now this is the square of the momentum operator, and to calculate the expectation value of p square, we have to evaluate this integral. This is an integral of psi x times psi 2 dashed of x dx from 0 to pi, and psi 2 dashed of x is sine of nx times some constant. Once we calculate the expectation value of p square and expectation value of p, then we can calculate the value of momentum uncertainty. Now let us look at the code. So in this portion, we import the necessary libraries. Next, we have some user-defined function which calculates the value of delta of t. So in this step, we define the wave function psi. This is sine of nx times some appropriate constant. This step, we calculate psi dashed, and in the third step, we calculate psi 2 dashed. And then here we calculate the first integral, psi times psi dashed dx. And in this step, we calculate the second integral, psi times psi 2 dashed dx. And finally, we calculate the value of the momentum uncertainty. And this value is returned. Now, in this code, we are calculating the expectation value for a range of values of n. In this example, we vary n and find out the expectation value. For example, we vary n from 1 to 100, where n equal to 1 is the ground state. And then we also calculate the momentum uncertainty for excited states up to a state n equal to 100. So here we run a for loop and we get the value of momentum uncertainty for various different values of n. So here we call the function f of I, and then this is done for n equal to 1 to n equal to 100, and then we store the values of the momentum uncertainty in this array. And after that, we plot the value of momentum uncertainty as a function of n. Let us see the code. So this is where the libraries are imported, and then this is the user-defined function that will calculate the value of momentum uncertainty for a given value of n. And this is where we run a for loop and get the value of momentum uncertainty for various different values of n. And this is where the values are plotted as a function of n. So let us run the code and see the output. Thus, we got the plot of momentum uncertainty as a function of n. And we see that the momentum uncertainty is increasing linearly with the value of n. You should match the result with whatever we have learned in the theory part. Let me quickly summarize what we have done. so far and also tell you what you are supposed to do with the codes shown in the lecture. First, we have plotted the probability density for eigenfunctions in particle in a box. You can use the code to plot mod psi n x square for any given n. Next, we calculated position uncertainty for a given n. We derived the analytical result during the theory lectures, and using the code, you can check whether the numerical and analytical result is matching or not. Also, you can use the code to check for the asymptotic value of delta x. What do I mean by asymptotic value? In the equation of delta xn, if you put n equal to infinity, that will give you the asymptotic value. Next, we calculated the momentum uncertainty starting from the ground state to some excited state with n equal to 100. Again, you can match with the analytical result derived in the theory lecture, and that turns out to be delta Pn is equals to n h bar. And you can match this with the plot we got numerically, and then you see that it perfectly matches with the analytical value.